Hey everybody, in this next video lesson, we're going to talk about a concept known as neutralization. I'm also going to show you the calculations that are involved in neutralization reactions between acids and bases. Let's begin with the concept of neutralization. Acids and bases are essentially opposites of one another when it comes to water equilibriums. When they are combined chemically, they will neutralize each other, or basically reduce each other to nothing more than water and salt. When it does it, it might also absorb or release a significant amount of energy. Typically, acid-base neutralizations come along with a fairly large energy change as well. Now, in this class, we are not going to deal with any equilibrium situations. We're going to just go forward reactions only. For example, NaOH, which is a base mixed with HCl, an acid, will produce water and salt. Now, water, in this case, I will put HOH because it's the H from the acid and the OH from the base, but you know that if you combine H's, you get H2O. But a salt could be any ionic compound. Could be sodium chloride, could be potassium bromide. It all depends on kind of what the cation is of the base and the anion is of the acid. Another example would be a base like NaOH, has the OH, and the H from HC2H3O2. This is acid in the form of acetic acid. This is vinegar. So the H from the vinegar and the OH from the ammonium hydroxide makes water, HOH. And then the other substance, the salt, in this case, would be ammonium acetate. Now, if a neutralization forms an equilibrium, this is what we call a buffer. The chemistry behind buffers is pretty complicated and pretty complex, and it is a topic that we cover in AP chemistry, but it would require a whole nother module's worth of information. And for that reason, we're not going to talk about any situations in which neutralization forms an equilibrium. We'll leave that for AP chemistry to tackle. When a neutralization happens, the chemical reaction that occurs is actually just a double displacement reaction. But in this double displacement reaction, instead of producing something that's aqueous and in something that's not aqueous, in other words, insoluble, we produce salt and water. So a double displacement reaction takes the cation of the acid, which is the H, and the anion of the base, which is an OH typically, and forms water, and the rest of the stuff results in a salt. Now, when both the acid and base are a strong acid, the neutralization will always result in a neutral pH, meaning when they neutralize each other and you have equal amounts of acid and equal amounts of base together and they neutralize, the pH will be 7. But if one of them is weak, it will not produce a neutral solution. And this is an observation that is important, and you'll have to know this for the upcoming quiz. But a weak acid or base only partially ionizes in solution. The stronger the substance will dominate the pH. So if you have a stronger acid and a weak base, the pH will be less than 7. And if you have a stronger base with a weak acid, then the pH will be above 7. And you're going to have to be able to memorize what happens with the strong and weak combinations. So make sure that you make some flashcards or study this slide pretty carefully. If it's strong with strong, pH is 7. If it's strong acid with weak base, it's less than 7 on the acidic side. And if it's a strong base with a weak acid, then it's greater than 7 or on the basic side. At this point, I want to take you over to a simulation that shows what happens to the pH when you mix acid and base together. So check it out. You're looking at a titration simulator, and we're going to do a lab that looks very similar to this setup next week. But I wanted to show you this simulator to kind of explain to you or show to you what happens when you add acid and base together and what it looks like when the pH changes when acid and base are mixed. So the first thing I need to do is I need to choose an acid. I'm going to choose hydrochloric acid, and I'm going to make the molarity 0.1 molar. Now I'm going to choose a base that's also strong. I'm going to first show you the strong acid and the strong base combination. Now I need to determine or choose which one of these goes in the burette, and I like to put the base in the burette, and that means the acid is then down below. Now the burette is this long skinny thing on the left hand side of the screen, and down below will be the acid. I want to choose an indicator, and I'm going to choose phenolphthalein. That's the one that starts clear in an acid and turns pink in a base. I'm ready to add the solutions to the burette and begin the experiment. Now I'm going to touch the burette and it's going to start dripping. And as you can see, the acid starts out at a pH about 1, and as the base gets added, the pH increases little by little. I'm going to pause it at this point. Take a look at the burette reading up at the top. I've now added 8.9 milliliters of the base to the acid. The acid is still clear, which means that we haven't reached a pH of 8, which is where the phenolphthalein changes color. Currently, the pH reading is 1.61, so it hasn't gone up very much. Now when I continue adding the base, the pH continues to go up, and I'm going to pause it once again. Now my pH is about 2.8. I've now added 11.52 milliliters of the base to the acid. Now at approximately 12.5 milliliters, you're going to see the pH change significantly. Even just a few drops and it's going to go up pretty quickly. So I'm going to slow the drop rate down here so you can see this happen a little bit more clearly. So we've got the drops happening much more slowly now, but the pH is going up. Now right about here, you're going to see a few drops cause the pH to go significantly upward. At about 13 milliliters now, the pH went from about 2 to about 10. That is how we know that the equivalence point has been reached. That is the point at which the moles of acid that started out in the beaker are equal to the moles of base that got added from the burette. Now I'm going to let this drip continuously, and you can see it marks the equivalence point. The equivalence point on this curve is identified by the steepest portion. And since we are mixing strong acid and strong base, we talked about on the previous slide that the equivalence point for this will be at 7 pH. And it is at 7 pH. If you go that vertical blue line down to where it stops and then over to the left, you'll see that the pH is 7. Now I'm going to stop dripping the base into the acid, and we're going to end this titration. That is what this is called, a titration. So in summary, you start with an acid, you add base to it, and the base neutralizes the acid a little bit at a time, a little bit at a time, a little bit at a time. Eventually you get to a point where the base neutralizes all of the acid, and at that point the red curve swings drastically upwards. This is what is known as the equivalence point, or where the moles of acid equal the moles of base added. And that is happening at a pH of 7. Now I'm going to reset the simulator, and instead of hydrochloric acid and sodium hydroxide, I'm going to use a weak acid this time. Acetic acid is a weaker acid than hydrochloric acid is, and the base I'm going to keep the same. Now, because we talked about this, this is now a weak acid strong base combination. And if you remember from the previous slide, we would expect the pH at the equivalence point to not be 7. Let's take a look. Everything else is the same once again, and I'm going to add base to the acid at a rather slow rate. You can see that the pH begins to increase because we're adding base to the acid. The acid is getting neutralized, turning into salt and water, and the pH increases because the concentration of acid goes down, the concentration of base increases, and so we get a pH that starts to creep up towards 7. Now I'm going to pause the titration at this point and take a look at what's happening. And we've added 6 milliliters of base to the acid. It's still clear because the pH is still below that 8 threshold at which phenolphthalein goes from clear to pink. Now I'm going to increase the drop rate a little bit so that this goes a bit faster, and I'm going to go ahead and start the titration again. Now the burette will increase volume reading, the pH will go up, and right about 12 to 13 milliliters, I stopped it just a little bit short, but you can see that the red curve is about to turn up. And now I can slow it down, add a few more drops, and you can see the curve go zoop, straight up in just a matter of a few drops. The solution turns pink. We've reached the equivalence point. And the thing I want to point out at this time is that if you take that blue line that represents the equivalence point, drop it down until where it ends, and then go over to the left, notice that the pH is not equal to 7. The pH is much higher than 7. In fact, it's about 8 or 9. And we would expect that based on the notes that we saw from the last slide. That because we have a strong base and a weak acid, at the equivalence point, the pH is going to be closer to the substance that is of the strong variety. So the stronger the base, then the acid, then the pH at equivalence is going to be slightly basic. And the opposite would be true if you had a strong acid with a weak base. The pH would be on the acidic side because the acid is strong, the base is weak, and the equivalence point pH would be less than 7 in that case. So I just wanted to show you what it's like when you add acid and base together and how the pH changes as the volume gets added. Now I'm going to take you through the calculations that you need to know in order to do math or stoichiometry with acid and base neutralizations. The calculations involved here are nothing more than solution stoichiometry. If you remember back in our stoichiometry unit, we talked about how you can use the molarities as a conversion factor. And we've got a molarity of a base and a molarity of an acid. And so we can do liters to liters stoichiometry. It's liters of substance A converted to moles of substance A, converted to moles of substance B, converted to liters of substance B, where A is what you know and B is what you're trying to find. So this is going to require two molarities, which we have, base and of acid, and a starting amount, in this case of base, and we are solving for milliliters of acid. Now you could do this stoichiometrically, and I'm going to show you the math involved, but I'm also going to show you a shortcut formula that you can use, which is something that I've used to teach my students in my AP chemistry class, and it's actually much simpler to use than stoichiometry. And what it is just a plug and chug sort of thing where you stick your numbers in and solve for the missing variable. So it does stoichiometry without actually doing stoichiometry. So because this is stoichiometry, we need a balanced chemical reaction. And the balanced chemical reaction is this. You've got HCl plus NaOH gives you NaCl plus H2O, right? Salt and water. And this is in a 1-to-1 to 1-to-1 mole ratio. And so everything's in a 1-to-1 ratio. Next, I need to set up my stoichiometry. And I'm going to begin with 10 milliliters, but I need this to be in liters, so I move the decimal 3 times to the left, so it's 0.0100 liters. Now I'm going to multiply that by the molarity of the known substance, which in this case is a base. So it's 0.550 moles on top and 1 liter on the bottom, because we need to convert from liters to moles of NaOH. Next, I'm going to do the mole to mole conversion, which requires 1 mole of NaOH on the bottom and 1 mole of HCl on top. Finally, I'm going to use the last molarity, which is of hydrochloric acid. This time I want the 0.250 moles to be on the bottom, and I want 1 liter on top because I'm asking for how many milliliters or liters. Then I can convert to milliliters at the end. So once I've got all that work set up, I can punch it in my calculator, and the correct answer is 0.022 liters or 22 milliliters. Now, as I mentioned, that's the stoichiometry way, where you take liters to moles to moles to liters. But as I mentioned, I've got a little bit of a shortcut that basically takes all the stoichiometry and turns it into an easy formula to remember. You just plug in all the known values and you solve for the missing variable. And so I'm going to introduce that to you right now, and it's going to look like this. It's MA times VA over NA equals MB times VB over NB. Now what M is the molarity of the acid, and V is the volume of the acid. N, in this case, in the denominator, is the stoichiometric coefficient for the acid from the balanced chemical reaction. The same can be said about the MB, the VB, and the NB. These are all for base, and the ones on the left are all for acid. So you'll be able to get 5 out of these 6 numbers, and you just solve for the missing number. And hopefully, if we do that, we'll get 22 milliliters in the end. The other thing about this is that because I don't need to convert to liters in this case, I can leave my volumes in milliliters and I get the same answer no matter what. And so here's how I do this. I take the molarity of the acid, which is 0.250 molar, times the volume of the acid, which is my unknown, over 1 because the stoichiometric coefficient for the acid is 1. Next, I want to take the molarity of the base, which is 0.550 molar, and 10 milliliters of base. And once again, the N value is 1 for the base, so I put 1 in the bottom. Now, the only thing that I'm missing is VA. So if I take MB times VB over MA, isolating VA, I get an answer of 22 milliliters, just like I got using the stoichiometry method. It's important to note that if the numbers on the stoichiometric coefficients are different than 1, then of course you have to change them down here, and that's going to affect your final answer. But because these were 1, you can just simply put 1s in the bottom. But as you can see, if I use this formula that I've written in red and just plug in the numbers that I know and solve for the missing number, I can get the same answer even if I do it using stoichiometry. So you have two options. You can do the way in blue, which I showed you using traditional stoichiometry, or in red, you can use Mr. Calmey's patented solve for the missing variable method. So let's finish up with a few practice problems here. Now, I've got 25 milliliters of 1.5 molar H2SO4, and it says how many grams of KOH are needed to neutralize the H2SO4. I'm not going to be able to actually use Mr. Calmey's patented solve for the missing variable because that only works if I have molarities and volumes of both my acid and my base. But I'm looking for grams of base this time, so I'm going to have to use traditional stoichiometry. But before I do, I'm going to need to write a balanced chemical reaction between the neutralization of acid, H2SO4, and KOH. So I'm going to do that right here. So as you see, I have 2 moles of KOH for every 1 mole of H2SO4, and so my mole ratio here is not going to be a 1-to-1 ratio, it's going to be a 1-to-2 ratio. Go ahead and pause the video now and see if you can solve this one without me, and then restart the video and see me work out the answer. Pause the video now. Alright, the first thing I'm going to do is I'm going to start with 25 milliliters of my acid, but I need that in liters, so it's 0.025 liters over 1, and I'm going to multiply that by the molarity, 1.5 moles of H2SO4 over 1 liter. Next, I need the mole-to-mole ratio, and once again, I want to put the H2SO4 on the bottom, so I'm going to put the 1 on the bottom for H2SO4, and I'm going to put 2 moles of KOH on top. Finally, I'm going to use the molar mass of KOH, which is 56.11 grams per mole. I'm going to put the grams on top and the moles on the bottom. And so now I've got the stoichiometry all set up. So if I put this into my calculator, I get an answer of 4.21 grams of KOH. And that's how much of the KOH I need to add in order to neutralize this acid. Now in this last one, I've got a molarity of a base and I've got a volume of a base, and I have a volume of an acid, and I'm asked what's the concentration of the nitric acid. So I can use Mr. Calmey's patented solve for the missing variable method here. Before I do that, I need a balanced chemical reaction. As I read the problem, I've got a base mixed with nitric acid, and if you remember, nitric acid is HNO3. So if I write a neutralization of nitric acid, it's HNO3 plus NaOH gives you water plus NaNO3, and everything's in a 1-to-1 mole ratio. So now I can set up Mr. Calmey's patented solve for the missing variable method. We've got a molarity of the acid, and that's my unknown. It says what's the concentration of the nitric acid, so that's my X, and I multiply that by 25 milliliters, and I'm going to put that over 1 because the stoichiometric coefficient is 1. Now I'm going to set that equal to the molarity of the base, which is 1 molar, times 45 milliliters, also over 1 because the stoichiometric coefficient for the base is 1. And all I need to do is solve for X. When I do that, I get an answer of 1.80 molar, and that is my molarity of the unknown acid. So I left you with 2 practice problems here that you could try in your notes, and also there's some practice problems in the student files that you can work on using stoichiometry if you want, or you can use the solve for the missing variable method. Remember, you can only use the solve for the missing variable method that I showed you down here in red as long as you know 2 molarities and 1 volume, or 2 volumes and 1 molarity. But if there's any part that asks for grams or gives you the grams to start with, you cannot use this formula. You'll have to use traditional stoichiometry. Well, that takes care of this video lesson. Thanks for watching.